Holy crap, there's a lot of people here. Hi, I'm Kyle. Thank you for coming to this talk. This is a talk that I've been wanting to do for a while, and hopefully I haven't completely screwed this talk up. It covers a lot of very crazy new technology that I'm becoming very, very interested in, and I'm going to get into kind of what's going on and why people are doing it, like kind of what motivates them, and introduce you to sort of like various number of tools that and pieces of software that people are kind of using to try to implement this idea, which I think could be a potentially very big idea. So I want to just give a special thanks to New Relic. It's really nice to be able to use this space for events and meetups and things, and they've been super helpful in helping Portland Tech out. So thank you, Christian, and thank you, New Relic. And please clap. And I also want to thank Control H, which is a newish hackerspace up in North Portland that has been letting me install a bunch of crazy distributed web things in their server rack, and they've been very nice to me. So, yeah. So this is, I don't know how many people actually brought laptops. We can maybe do this later, but there is you'll notice a Wi-Fi access point up here. And if you connect to it, it is CJDNS as the Wi-Fi, and you run brew install CJDNS, and you run these two random weird-looking commands, you will be able to actually use a distributed routing system while you're listening to my talk. It looks like most of you don't actually have laptops open right now, so you actually want to listen to me talk, which is weird. I think you're going to regret this decision, but anyway. I'm happy to show you CJDNS later, and we can get back to this, and I'll show you some random things. Yeah, I'll run Linux. Oh yeah, no, there's Linux instructions are like, git clone and then like run a bunch of weird commands and stuff. So go to their GitHub and, but it's pretty easy to get up and running. But we're not just talking about CJDNS, we're talking about all kinds of other stuff. We've got a lot to cover, so please hold any questions till the end, just so we can kind of get through everything and be done. So I wanted to talk about this really quick. So there's no way I can start this talking about the distributed web before talking about cryptography. Like literally, as I was doing my slides over the last week and a couple of weeks, we have gotten a lot of people worried. People like Bruce Schneider that are worried that we're entering essentially crypto wars 2.0. And so I wanted to give some context because I don't know how many people actually know about the crypto wars and kind of understand what that is and why people are starting to get worried about it again. And the way I wanted to introduce you to this concept is this guy who, for 1996 standards, looks pretty cool in this photo. But this is Phil Zimmermann. Phil Zimmermann was the inventor of the Pretty Good Privacy project. Now this was, he certainly wasn't the inventor of like public key cryptography. That was really Diffie-Hellman, who recently won an award for it. Actually, I don't remember the first names. Sorry, they're Diffie-Hellman, and but he was the first one. So at the time, there was, in the mid '90s even, there was a time when cryptography was very weak and very bad, and it was kind of somewhat intentionally kept this way so that it would be possible to brute force it by government organizations that were large enough to actually do it. The first person to really kind of make the killer app of cryptography, really take strong cryptography and make it public to a large extent and get people to start using it and thinking about it was Phil Zimmermann. And so I wanted to just give him a plug and introduce you to him tonight because it is, that is the reason, before, PGP started, before that, most cryptography only had like 40 bits of encryption, which is, not very strong. PGP, you couldn't go lower than 128 bits, and really, I think the default was like 256 bits of encryption, of I guess, key space or whatever. And the important thing about this is that when it's 128 bits or more of a private key, I'm trying to describe this without getting into like mathematics and stuff, sorry. Which I don't know most of the mathematics of it, actually. It's a very, very complicated topic. But the thing is, the thing about it is that, what they're talking about in the news right now is that when you use how many people use iPhones here? Hands up for iPhones? Wow, like everybody here is using an iPhone. Okay, cool, like most people. When you enable encryption on that phone, when you enter in a pretty decent password and you encrypt that phone, nobody can get access to it without that password, unless it's a really bad password, and then they can just brute force it. So don't use like the word cat or something like that, right? But that's what they're talking about. We're entering a world now where where governments can't, without you typing in your password, they can't decrypt your phones anymore. And this is what they're talking about when they're kind of being like, we need to put backdoors into iPhones and stuff like that. This is a very interesting thing because there isn't really a lot of precedent here. I mean, there's a lot of argument that cryptography is freedom of speech. And in fact, one of the ways that Phil Zimmermann demonstrated that is you'll notice that there's a book, and that book is a copy of the source code to Pretty Good Privacy. And MIT Press published it. And so the idea was that you could rip even if they banned cryptography or like declared it as like munitions and you couldn't export it, you could still rip the book apart, scan all of the code in, and compile strong cryptography. So, I mean, that was the idea behind that. And didn't really set any precedent with that, but it was just kind of, it's kind of interesting and made a point. And if you try to find that book on Amazon, there's like used ones for like $1,000 and stuff. So to give you an idea of like how significant this book is. But yeah. So moving on, I started a site called NeoCities. The idea behind it was to bring back free websites, bring back the idea of people creating websites, not having like a WYSIWYG editor where like you get a template and you just put your text in it or whatever, but like actually creating like entire websites from scratch. That was something that I thought was kind of lost in the current web. We're kind of increasingly going into like social networks and stuff. Everybody thought it was kind of this like anachronistic joke at the time. It was a lot of like under construction GIFs and like fake GeoCities web pages and stuff. And part of even I didn't think it was going to last more than like a month. I just assumed that something was wrong with the idea and it's going to blow up in my face within like a month or two. But that has not been the case. It's been growing pretty substantially since I launched it. And actually, it's not 60. It says 69,900 sites on the front of this image, but actually it just hit 70,000. So we're getting a lot of sites on NeoCities. Thank you. It's definitely something that's catching on. And now, so at the same time that I was working on NeoCities, I was working on some kind of Bitcoin-related stuff. I worked on a pretty early web wallet called CoinPunk. I also did some work on Bitcoin.js, which was sort of the library implementation of it. Assuming that these two projects I was working on would never have any connection to each other at all. Well, fast forward a few years, and the ideas are starting to converge. Like my work with Bitcoin and my work with web pages is starting to kind of converge into a single thing, and that's what's been getting me really interested in the distributed web. Now, I'm going to try to describe to you how the distributed web works in a little bit here. But I want to try to kind of distill this down into something that, because I mean, there's not really a name for it yet. It's some people call it the permanent web. I've been calling it the distributed web. But it's a web that enables community-powered websites that have no central point of failure. As in, like, it's not run by a central server or an entity. It's not controlled by one group. If you make a web page and some other people like that web page, they can help. They can not only bookmark your site or share it on Twitter or whatever. They can actually help you to serve the site. And so that's the really interesting thing where it converges from I like this thing to I like this thing so much I'm going to help persist it. And it's not a theory. It's already here. And I'm going to show you sort of the genesis of it right now. So there's a lot of motivations for doing this. One of the motivations is sort of this idea that, which I strongly believe that the web we have is eroding right now. When you go to a website and it's usually not there in 10 years. Most of the history of the internet from the 90s is essentially gone. I mean, it's either the company went out of business or the person that made the site decided to stop paying their bill or basically we're losing our history, and one of the things that distinguishes Renaissances and Dark Ages is simply that, a lot of other things, but, it's not simple, but it's that they're, it's that they're not, when the Dark Age, you don't, sometimes the Dark Age can be as simple as they were writing on something that didn't stick around for a while, when the Egyptians, for example, used papyrus scrolls, or whoever used papyrus scrolls, they just tend to last a long time, and we're fortunate that they did, because otherwise we wouldn't have recorded history from a lot of these civilizations in our past, and we wouldn't have been able to learn from what they experienced. So this notion of like making a distributed Library of Alexandria and kind of dealing with this like erosion of our history problem, which is that we have right now. You know, the Internet Archive down in San Francisco is doing a very good job of like trying to do their best to do this on their own, but it'd be really nice if we could be able to assist them in some way in that process, and you know, not have it so that the entire history of the web is literally being run on a couple of data centers in San Francisco. You know, it's kind of an earthquake-prone neighborhood. You know, as Portlanders, you might know what that's like. Other motivations that are more political in nature. Increasing corporate power over our lives, the idea that these social networks have injected themselves between us and our friends, and that contract is kind of arbitrary. It's this notion that yes, it's free, but it's they control everything and they can make changes to that infrastructure that may or may not benefit you. And a lot of people are obviously getting a little nervous about that, like a little, not necessarily nervous, but just like skeptical of like, a natural skepticism of this thing that's like there and like they don't have a lot of control over in their lives. The NSA has been basically sniffing, all kinds of, data on the internet. It's gotten to the point where paranoia is like crossing into reality, and I can't tell the difference between the two anymore. I mean, I've even heard rumors that there's like NSA like kind of like specific buildings in town that are like the NSA has their monitoring stations here and stuff. Like I've heard these stories and I just can't even rule them out anymore. It's like political censorship and extremism, not such a big deal in the United States, but obviously in countries where political expression is not as tolerated. It becomes a lot more difficult to propagate information through those services when they're just blocking off. If you're organizing, a revolution on Facebook in another country and they block Facebook, it doesn't do you a lot of good. And obviously, actually, the biggest free speech issue in this country is intellectual property laws. Actually, because they've been given an extraordinary amount of power over copyright that favors the producers. I mean, the original intention of the whole idea behind copyright was that it was only supposed to last about 14 years or something like that, and now it's like 140 to 160 years, depending on how healthy the person that created the work was at the time or whatever. So and yeah, the NSA. But more to the point, I mean, it's just, this is kind of a lot of the way I get into these ideas is simply that they're really interesting. I mean, it's an interesting tech. A lot of people are using this technology because they can. It's a really interesting thing to kind of explore. It's a new thing that we know how to do now, and we didn't know how to do it before. And like, what are the implications of that thing? This is the way I like to approach problems like this. I mean, when I was getting into the Bitcoin space, I wasn't like, everybody sell all of your money and dump it in Bitcoin right now. Like I said, this is probably a commodity money. And that was my talk. I did an hour-long talk on just Bitcoin as a commodity money. It was intensely boring, but at no point in it did I say it was a good idea. Like there's a difference. You have to separate the technology and the ideology for your sanity. So, the original design of HTTP and the web was that it was supposed to be sort of decentralized, like this chart on the right. But what we're seeing a lot more often now is this kind of teetering towards centralization as we get into like, IRC turns into Slack, like email turns into Facebook or Twitter or whatever. This seems to be like not stopping. It seems to be kind of amplifying lately. And in fact, if you look at charts of like that are not just like those sort of like global village like links of computers to each other, and you actually look at like the amount of like influence that those links have, you start to see these sort of like black holes in the universe that are like kind of slowly getting bigger and eating all the other stuff. And that's I expect these bubbles to continue to get bigger over the next 5 to 10 years. I mean, it's the trend. There's another kind of thing that really bothers me. This is probably the most extremist slide in this deck, hopefully. So I'm not trying to be too political on you, but one of the things, when I look at Facebook, this is what Facebook looks like to me. It's like this incredibly centralized thing. Everybody's kind of fit into these same little slots, and these little apartments that are your profile wall, and you can make a couple little kind of insignificant changes to it. You can like change the background photo on the top of the link or whatever, or of the profile, and you can change, and then on the left there's like the where do you work, where did you grow up, and there's only like 4 or 5 things, and most of them are things I wouldn't really want to project to people. Like it's not something that's important to me. Like where did you go to college? But it just kind of, and then of course there's this like kind of centralized leader that runs the whole thing, which is Mark Zuckerberg. So like this picture just kind of, I look at it and I'm just sort of like, oof, that kind of hits close to home. But in practice though, the way I look at the internet isn't, and the web, it isn't this bad for me yet. Like I don't look at, it's not that terrifying to me. The internet to me right now is, it looks more like Hong Kong. It's this, Hong Kong used to be, maybe it still is, it used to be one of the sort of like civilly and economically free countries in the world. It was, essentially, to give a context on this, in the sort of 50s and 60s, their Treasury Secretary was this guy named Sir John Copperthwaite, and this guy was so hardcore. He was like, we don't even have conversations about his school of economics anymore. He was an Adam Smithian, like hardcore, like Smithian classical economist, and no joke, he slept next to a copy of The Wealth of Nations. Like that was his Bible, and Hong Kong at the time was kind of like the sort of like the freedom reaction to China, and we got to kind of see what happened as a consequence of that, and so it's very good as like a study, whether you agree with that political system or not. It gives a nice contrast for like all the other, I like countries that do weird experiments, because then we can learn from those experiments, and the thing is though, is that Hong Kong's kind of in that situation where like the freedom of that country is kind of in question right now, because China's been taking over the country, and they're slowly sort of eroding a lot of the civil liberties of the area. They're encroaching into a lot of the economic contracts and the business community there. And there's a real question that Hong Kong might, there's actually a city in China that's not very far away from Hong Kong, and the way things are going, that city's going to be like 5 times bigger than Hong Kong in the next 20 years or something like that. So there's a lot of sort of things, like Hong Kong might not be the biggest city in that area anymore. It might be like a suburb of another city over there. So, to me, the internet's like this. It's like, we're at this point where like, it's starting to kind of get a little authoritarian and weird. And, what are the consequences of that? Are they bad? Okay. So a distributed web changes the power dynamic. Servers and clients essentially become nodes. We get rid of this notion of like, here's your web browser. It only loads a page and executes the orders of the server, and you get this notion of like, here's a node. Everybody in this room, if everybody in this room was using the distributed web, everybody's computer would be a node on that network, essentially cooperating to help distribute information. That's, instead of like what we have where there's just giant data centers, right? Like go over to Prineville in East Oregon, and there's just these enormous data centers, and they have all the information in them. So it really kind of separates that into like a more distributed fashion, where like we all get to help to chip in to a small part of the web. And that sounds really kind of like, oh, you mean like on my laptop? That's pathetic. That's puny. But if you think about it, if all of our computers and our like home servers and stuff, if we combined all of these into a network and they were all helping to assist it, this system would be far more powerful than anything that we've ever created in a data center. We're talking about tons of, immense amounts of storage, immense amounts of bandwidth. It becomes very difficult to like censor things by blocking them at the country border, because now the nodes are inside the network. How do you block that? So it really changes the power dynamic of what we have right now, which in a really interesting way. So I want to get into the core technologies that are making this even possible. And the reason why is because if I don't get into them, it's going to be very hard to understand them. Now, I'm probably going to screw this up, and you're going to learn almost nothing about cryptography today. So I'm just warning you ahead of time. But I'm going to try very hard to kind of give you a crash course in what you need in cryptography. Just the basic kind of constructs of like what you need to know in cryptography in order to understand the concepts behind this. And there really is only a couple of things. Like once you learn a few things about cryptography and how it works, the rest of it is pretty straightforward. So cryptography crash course. So the first thing I want to introduce you to is cryptographic hashing. Now, essentially what this is you take any information you want and you run it through what's called a cryptographic hash function, and it spits out a digest, which is the thing on the right. you'll notice that all of the digests are completely different on all of these. The only way that they'll ever be the same is if you feed the same input into them. And the size of the signature that they give you is the same size, and it's all very, it comes out in a nice consistent signature every single time. And if that ever changes, like it's essentially broken. Something's wrong with it. But this is sort of this is a very important thing. Like any data goes in, comes out as a digest, and this is the other important thing. You can't reverse it. So if you see a digest here, you can't figure out that it's the word fox unless you try to brute force it. Now, the brute forcing of the word fox is going to be a lot easier because you can just throw a dictionary attack at it and just like list all the dictionary, all words in a dictionary and just try to guess it. But actually brute forcing this, if it's like a long and complex thing, becomes very difficult. And I'll get to that in a second. I first want to introduce to you the quad guitar. This is a beautiful, beautiful piece of machinery. And I want to take a hash of a screenshot of it. And this is, so I've taken this image and I've just fed it into a cryptographic hashing function or whatever, and spit out this digest, which is this string will always represent this image. Now I'm going to show you the same image, right? Now keep it, so this one starts with FD1C, right? Notice that they're different. This is an image, but it has a different hash on it. The reason why is because I opened a text editor and I changed 1 bit in this image, and 1 byte actually technically, and this made the hash completely different, even though it looks the same to us, right? So one of the things, there's a lot of kind of wonderful properties you get from this. One of those properties is that you always, if you have this hash, you can always verify that this image is the one that you're looking for. As long as you have that hash, if you try to communicate with some random computer on the network and ask for this data, this image, and it sends you the wrong image, you can use this hash to determine that it sent you the wrong information. So that's really important for example, detecting malicious code and things like that. Like if you release a piece of software and then you get a signature of that software and then that signature changes, that somebody has modified it and maybe put a virus in it or something, or like a Trojan horse. It's actually happened to, I think, Transmission last week, a big BitTorrent client. Somebody hacked into the server, threw some malware in it, and yeah, the signatures are how we understand that something's wrong. So if you're like running apt-get install on Linux or brew install or whatever, and it's complaining about the signatures, don't let it continue installing because there's something wrong. Make sure that it gets checked out. So that's cryptographic hashing. That's the first really important thing. The other really important thing is public key cryptography. And so basically when you create a private key on your computer, you're just kind of, you literally, there's this thing in your computer called an entropy pool. And essentially what it does is it spits out random data. It's not truly random, so we call it a pseudo-random number generator for that reason. It's fed from all kinds of stuff. When you every time you type a key, the current time, every time a packet comes into the network. The Intel has a randomizer on their chip now that everyone thinks is like secretly like controlled by the CIA or something. But again, it's just like it doesn't, and somebody actually started a campaign to try to like get that out of the Linux kernel and not support it. And the guy on the Linux kernel that works on it was like, you're nuts. Like, shut up. Seriously, you're crazy. You don't understand how this works. Because again, like the Intel chip just feeds into this entropy pool, and there's enough crap in the entropy pool where it shouldn't be a problem. But anyway, what it does is it generates a private key. And if it's an elliptic curve private key, it can be like, I don't know, like 128 bits or whatever, right? You can generate much larger keys. You can generate ridiculously large keys. Now, the thing about 128-bit elliptic curve keys is that it's impossible to brute force them. As in, it's possible, but it's one of those things where you get into the realm of like theoretical physicists doing crazy math on a whiteboard to figure out how crazy the proposal is. For example, with 256-bit keys, there's this, essentially like it goes like this. I actually read this from a theoretical physicist or somebody. He was like, okay, so if you take all the energy in the solar system and you like throw it into a Dyson, create a Dyson sphere around like a giant pile of like fusion energy coming from the sun or whatever, and have the most theoretically perfect computer ever made, then it'll take you like a billion years to brute force it or something like that. I mean, it was like even 128 keys are just like, it might be possible if all of the energy in the world was like if the entire planet Earth was converted into a giant computer that was like the most efficient computer you could theoretically design, and it would still take like 40 years or something. Like it's just crazy math like that. So the only real way to break a private key is to break the cryptography, and from what we know, or to put a backdoor in it. But from what we know right now, this is pretty safe. Like most of the cryptography we use today that's 128 bits and up, we're pretty confident that it's not like, instant break, crack kind of technology. Now that private key is very important that you don't give other people that private key when you generate that, because that private key is what prevents someone else from doing the things that you would do with that private key. So yeah, it is like a private key, like the key to your house, right? If you give that key to someone, like they can go into your house and they can, do whatever they want. The public key is the thing that is derived from the private key, and the public key allows you to, well, essentially what it is if you give someone else the public key and you sign or encrypt data with your private key, you can send it to them in an encrypted way, and they will be only their private key will be able to decrypt it. So this is a really good way to like do like encrypted messages to other people. So this is just kind of a continuation on that slide of Bob wants to send something to Alice, and so Bob takes Alice's public key and encrypts the text "Hello, Alice." Turns into this just random unreadable crap, and then Alex's private key decrypts it, and then she can read the plain text. So that's basically public key cryptography. All right, so that's it. I mean, it's not it, but it's mostly it. I mean, that's sort of the basic building blocks of cryptography that you need to really start to dig into these crazy cryptographic systems that are being built right now and kind of start to understand them. For example, don't worry about reading through how the Bitcoin transaction works, but I mean, essentially, like Bitcoin is just a clever arrangement of public key cryptography and cryptographic hashing. I mean, there's a lot of other stuff in there too, but that's sort of the basic building blocks and, gets into most of cryptographic systems. So finally, distributed hash tables, which are the distributed hash table is how you send, it's how you essentially take information and distribute it over a peer-to-peer network. So remember those hashes, remember the hash of the image of the, quad guitar guy or whatever? If you ask for that hash on a peer-to-peer network that's using a distributed hash table, you can use that to retrieve that information through the network from anyone that has that information. The way that you can do that, even though these are random computers that you can't trust, is because that hash guarantees that the content that you receive, it will be verified, so that nobody can inject like something else in between that transaction. Or if they do, you can detect it. So distributed hash tables are incredibly efficient. They've actually, they're not necessarily new. GNU-Tella used them, which was sort of the answer when Napster got shut down. They made a GNU-Tella, which is sort of like a distributed version of Napster. They're very efficient. For 20 hops, you can you can talk to 10 million nodes on a network and ask them for information. That particular statistic is for Academia distributed hash tables. So distributed hash tables are sort of like the underpinning that allows a lot of this stuff to happen. Now, there's a difference here between immutable, I swear I'm almost done, immutable and mutable data. Immutable data is data that won't change. So the quad guitar image, right, that's an example of immutable data. You ask for that hash, you get the same image back. I want you to think about the key here in this distributed hash table diagram. What if the key isn't a signature of your, it's not a signature of like an image of the quad guitar guy. What if it's a signature, a digest, sorry. What if it's a digest of a public key? Well, now you can use the distributed hash table to find a public key, and using that public key, you can verify that, you can get references to information and use that public key to verify that information has been signed. And by the person that created it. So now you have a system where you can create mutable data which is sort of like when you create a website and then you make an update to it and have people be able to see the update. So that's what happens when you throw a public key into it. And okay, I'm done. That's my cryptography crash course. So we're over with that. This is a magnet link. So actually, if you've used BitTorrent before and you've used magnet links before, you've already used a distributed hash table and used a digest to find information and didn't even know about it. So if you actually look at a magnet link, you'll notice that there's just a big kind of long thing there, and again, it's just a hash it's just a digest of whatever you're looking for. And so this already works for BitTorrent. It's not this isn't an experimental technology. It's in production right now. People are using it. So distributed web. It's not a single project. It's not a single philosophy. What it is it's a lot of random people on the internet working on really random things that have some kind of connection to the other things, but not really. And a lot of this is just sort of like, when I started initially, it was kind of like, okay, how can we sort of like pick out things that we can, how can I get a full website? Because obviously when you have like you have a domain name, and then you have to put it on, you have to point it to a server, and then that server has to actually spit back content when you look at it. And like, how do you take all these sort of random pieces and put them together into a distributed system that will make a web page? There's a lot of different stuff, and I'm just going to go through and introduce all of it to you because it's all kind of interesting for its own reason. So the first thing is for domain names, there's this thing called Namecoin. Namecoin, was one of the first. It was actually the first fork of Bitcoin, and it was like in 2011. It was really early, and more importantly, it was a fork before all of the like crazy altcoin forks happened. Most of the altcoins are just literally they go in, they fork Bitcoin, they change it to like weed smoke fart coin, and then like put it up on the internet and be like, everybody give me your money or whatever, and it's just a scam basically, or it's like Dogecoin and it's a joke, but Namecoin actually isn't. It's a modification of Bitcoin to enable it to create a blockchain for domain names. So when you use Namecoin, you're buying a domain, essentially registering a domain using a private key, and there's no ICANN, there's no like domain registrars, there's no like top level root level domain systems. The entire thing is just completely controlled by the cryptography. And so there's no political way to inject into a website when you use Namecoin. If you have a domain that's a Namecoin domain, the only way for someone to really stop you from using that domain is to steal your private key, or force you to give them your private key, right? So it's very, it's still political. It's just political in a different way, The domains end with FutureTalk.bit. And one of the interesting, there's the tooling for Namecoin is not very good right now, honestly. Like, it's very hard to just run something locally on your computer in a couple lines that just automatically makes Namecoin start working for you. So instead, OpenNeek, which is the sort of like attempt to make a Google public DNS server alternative, they've started implementing Namecoin, and so you can you hook up to their name servers and start playing around with it. This is the one that I've been working with a little bit, called IPFS. There's a company called Protocol Labs that's been working on it. And this is sort of like the basis for the distributed web. It's, that sits on top of like, you can take a domain name from Namecoin and you can attach it to IPFS, and then you've got a full site. The idea behind IPFS is that it's this idea of making it so that data is very easy to distribute, and that it's very easy to publish content. And the way that it does this is with content addressing. And content addressing means that instead of like, so here's an example, right? When you type in website.com and you go to pathname.html, you're asking an arbitrary IP address on the internet for like a arbitrary human readable location name. There's no way to verify that content is what you expect it to be. It can change at any time, and sometimes that's what you want, but oftentimes that's not what you want. And that's not there's no way to really verify that information. Which leads to a lot of sort of stuff like this, where it's just like you're looking for content and it's just gone, which is the web erosion problem. So now when you use IPFS, you get a hash instead, and that hash represents the content that you were looking to receive. And so there's a sort of a nice little web interface for IPFS that you can kind of use for either on their IPFS.io site, which is literally just a node running for you for convenience sake. But you can also run IPFS on your local computer and do the same call. And in both of those scenarios, as long as there's at least one node on the entire IPFS network that has the information, you will receive it at some point in time. Like it will come to you. And usually it comes back really fast. I mean, when there's enough nodes helping to run the network, it's actually faster than like the regular web sometimes already. And it's really in an alpha state right now. So I just want to kind of also mention ZeroNet, which is another sort of similar idea that I've been looking at. It's been really interesting. Taking a very different direction. They're using a sort of BitTorrent's distributed hash table, the magnet link stuff I was showing you earlier. They're using Bitcoin key pairs for the mutable data. That's really interesting because it means that if you have a website on ZeroNet, that same private key can be used for a Bitcoin wallet, which means that people can send money to your website using Bitcoin just by knowing how to get to your site. So that's kind of cool. Also, they've integrated Tor already, which means it just, as long as you install Tor, it just works out of the box. Basically, as soon as you look at a page, you're assisting in serving the data. So I think IPFS in the long term has they're trying to build it from scratch. Have a system that's really specifically designed for it. And I can't tell you which one's better because honestly I don't know. But I do. If this is something that's going to be like a large replacement for the web that we use today, obviously it's very important that it's carefully designed and built for that purpose because it's going to be used by a lot of people in a lot of situations. Okay. So yeah, this is where I wanted to show you the mutable stuff, which is taking domain names and putting them on top of the distributed web. So it's not just a crazy, because obviously we can't remember the hashes, right? It's too long. You can't memorize it. So putting domain. So if you do this call, the node will actually look up the domain for you and retrieve and figure out. It actually asks the domain for a text record that has the hash in it. And so instead of using the domain name system for finding IP addresses, you use it for text records that represent the hashes of whatever content you're looking for. So that's pretty cool. Now I want to show you a demo right now. Hopefully it works. That is, this is ZeroNet, Tor, and Namecoin put together. This was the best I've accomplished so far at making a website as distributed as possible, using just kind of by goofing off on my computer over the last couple of weeks. So this combines these three into essentially well, so I actually did just the other day registered name FutureTalk.bit. So this is actually a Namecoin domain now. If Namecoin gets popular enough, let me know and I'll just transfer it over to you and you can have it. But yeah, here goes a demo. That won't work. This one will. These are going to be the same links, right? If I was running it locally, it would be, look at that. All right. So yeah, when you use it, it's kind of cool. I'm actually contacting someone else's random proxy that's also helping to persist ZeroNet sites. And you'll notice it kind of gives me this sort of interface on top of it that just kind of helps to deal with certain security issues and stuff like that. But because it's using paths instead of subdomains, and the way that browser security works is that if it's in the same kind of domain area, then it assumes that it's like the same server that's providing it and trusts it. So you need to put some code in to kind of protect ZeroNet proxies from websites accessing it and going nuts. So yeah, that's it. That is a completely distributed website. The only way to change that site or take it down or whatever would be to have the private key that I use to sign this this page and publish it. So yeah.
That you just display to all of us.
No. Well, it didn't have a private key. It's no, but it's actually not. So I was going to do a demo. Sorry, I totally knocked out my place here. I was going to do a demo of me updating that page on my laptop. And one of the funny things about it is that I would actually have to show you my private key in order to make that change. But the thing is that I can just throw the private key away and come up with another private key and point my Namecoin domain to it. So it's not really valuable to be able to like hijack that key. But yeah, it works. Like it doesn't work. It's a little slow sometimes, but it does actually work right now. Like the technology works. So I want to show you a couple other interesting things that I ran into. This one is a BitMessage. This is sort of like I can't figure out if it's a hybrid between email and like instant messaging, but the idea is that it's sort of using cryptography and a proof of work algorithm to build a distributed messaging client. And it actually works really well. It's just really surprising, actually. I mean, I actually used it to communicate with some people on the internet a few times when like that was the only thing they listed as their contact was BitMessage. And I'm like, oh God, like how's this going to work? But no, it actually works really well. And the idea behind it is to, make it so that, it's trying to be a replacement to email. Interesting thing about it though is that it's not trying to solve the spam problem because apparently it's not actually very, there's a proof of work algorithm that prevents people from like spamming the network with random junk and destroying it, but it doesn't actually stop spam because it's just, if you run the numbers, like basically spammers can just take over botnets and use it to, dump garbage onto people and stuff. So, but it works really well. It's interesting, but it's just an example of like, so it's the same idea, right? Private key, public key, you share the public key, the from spot here is again, it's just it's a hash of the public key, which we just kind of shortened to pub key hash when we're talking about them. But it all again, Bitcoin, IPFS, ZeroNet, BitMessage, they're all again just using those same sort of basic structures for, that I just showed you with the cryptography stuff. So this is the thing I was going to try to kind of show you tonight, or like have you play around with tonight. This is called CJDNS, and it's also the network that they're building with this is called Hyperborea. And essentially what this is it's a distributed IP routing system. It's a distributed sort of packet routing system. The way that it works is that it actually just generates an IPv6 address using your private key. So like I think it's just a hash. Again, it just takes like the first certain characters of your public key, or the first like n amount of data of your public key, and it just uses that to create an IPv6 address, because IPv6 addresses are just 128-bit in length. So you just you can just turn it into an IP. You can turn a public key into an IP address now. And so the idea is that there's not this central entity that's like assigning IP addresses to people, and there's not these central sort of like BGP protocol systems that are like deciding what the who gets where you go when you actually type in an IP address. So this is really interesting. It's not really, you can tunnel it over the internet. And what I've done here is this is OpenWRT hacked onto this wireless router. And it essentially what it does is it tunnels with some peers that have let me connect to them on the Hyperborea network, and allows me to sort of go through that process. Now, packet routing over tunneling over the internet is kind of weird. It's like, well, why would you do that? The real reason you'd want to use something like CJDNS is if you were getting into mesh networking. So this is actually when I started doing distributed web stuff, I kind of like randomly ran into the mesh networking crowd in town, and had like no idea like why why this had any connection to distributed web stuff at all. But I finally met some people that were doing stuff, and I started learning about mesh networking, which was really interesting because I actually used to do pirate radio stuff, so it was, it just kind of reminded me of that a little bit. One of the interesting things about, actually the most interesting thing about mesh networking to me is that they're not breaking any laws. When they do so mesh networking in a nutshell is like basically you get enough people with wireless towers that are communicating with, that are peering with each other, and you create a network that's essentially like the idea of like a distributed version of what we use for the internet right now. Because if you think about it, the internet's really centralized, right? Most of us, hands up, how many people here get their internet through like Comcast, right? Yeah. How many through like Quest or CenturyLink or whatever the phone company is called now? So yeah, I mean, that's most people in the room raise their hand for Comcast. So most of us have a central dependency on the internet that goes through a single company. And so the idea behind mesh networking is like create, community networks that if they get big enough and there's enough people on them and there's enough bandwidth, could theoretically replace your internet connection. I don't think that's super plausible. Like honestly, like I think it's going to take me a long time before. I think it's going to be a long time and take at least a couple Terminator movies before we get into the idea of like mesh networking as like a thing that we're going to want to actually do a lot of. But you never know. I mean, politics changes, climates change. But the fundamental problem with mesh networking with Wi-Fi is that you only get a half a watt or something like that, and the antenna can only be so long, and you basically have to be line of sight. And one of the funny things is that I was talking with some people that were doing mesh networking in town, and they were like, "Can you talk to the New Relic guys? Because we could set up a wireless, or, a Wi-Fi connect, a mesh network node like right here, and it would just like talk to everything in town, having a tall node is really important because it really does have to be line of sight. But I've heard rumors that apparently the windows might have some kind of weird coating on them that like blocks it or something. I didn't get too far into it. It was really strange. Yeah. So this is a live map of the Hyperborea network. Now, a lot of the networks here are just like a couple of people just running it in their house just for fun or whatever. If you look at I couldn't find a picture, but if you look at a map of, these are just sort of like showing all of the sort of like links of the network. It's kind of being pokey, sorry. And you can kind of see there's a lot of machines. It kind of shows how many connections there are to each of the machines or the nodes. And there's actually a lot of people connected to it. And yeah, if you take a packet and you try to route it from like the end of this guy all the way over here, it knows how to do that. It actually can use the CJDNS protocol to communicate all the way through this entire network as long as you're connected to at least one node. So that's pretty cool. I mean, there's a lot. It's very experimental, but it's very interesting. Yeah. Oh, by the way, yeah, the map was of Europe. Like the entire country of Spain is a giant mesh net. I don't know what happened over there, but like they have a ton of nodes there. One of the things I've been told is that one of the nice things about European cities for mesh nets is that all of the roofs or all the buildings are generally the same height in a lot of the cities, so it becomes very easy to do line of sight because there's not a lot of stuff in the way. And then the last thing is something probably everyone has heard of, which is Tor. Tor is sort of this idea of, the idea is that you connect to a machine somewhere and then it routes through a couple other machines and spits out the other side. And the theory is that people won't be able to trace where you're coming from, and you get anonymity. All of these sort of other technologies will just kind of work on top of Tor. So Tor is kind of this just sort of like glue that just kind of sticks to everything in the distributed web to give you that anonymity if you want it. The obvious trade-off is performance. Tor, going through Tor is really slow. Is there a point to all of this? So I have to summarize all of this and like make a conclusion because I'm supposed to. Just like Bill Hicks. I don't know. The thing is that this technology is really interesting, and it's so like if people start using it, which they might never. We might people might decide, oh, we're not interested in distributed web, and it'll go away and it'll be gone forever, and whatever. But if a lot of people start using this technology, obviously it changes the paradigm of the web that we use today, and in really fundamental ways, and here's the most important thing, in very complicated ways that I don't understand, and most of us won't understand. William Gibson had an interview recently with Alex Pasternak over at a Vice Motherboard. It was a really, really good interview. It's on YouTube if you want to watch it. But it's, basically he thinks of technologies as drivers and ideologies as an attempt to steer. And, that would really hit me as like there was, I don't know, it just kind of resonated with me really well because this technology is so complicated that if people start using it, I can't tell you what the consequences of that are. You know, I think that we're going to try to figure out what those consequences are. We can certainly guess at some of them, but the question becomes, how do you steer technology like this? How do you control it? Because technology is kind of very hard to control, and it is kind of the thing that's driving our civilization. We live in look around, right? Like we live in a city that's completely built on technology. The city would not be possible without technology. Everything around us is technology. The steel beams that built this building, the sewage system, it's all technology. And really, the ideology just kind of follows and tries to explain and understand that environment for us. But what I do know for a fact is that strong cryptography is here. It's out of the bottle. It's on your iPhones. It's not going anywhere. We can try to, they can try to ban cryptography, but it's not going away. In the 90s, when there were export restrictions on strong cryptography, all of the Unix development happened in Europe and in Canada. Essentially, the only thing that those laws did was made it so that the United States was left out on strong cryptography until they finally loosened them in the later 90s. Whether we decide that you can't encrypt your iPhones or we have to put backdoors in them or whatever, it's not going away. People are still going to have access to it. People are still going to use it. And people in countries where they don't have the same laws are going to still work on it. So the genie's really out of the bottle on this one. The distributed web is here. It's getting bigger. Does that mean it's going to become huge in the next couple of years? I doubt it. But, next 5 to 10, maybe. And, we'll see what the consequences of that are. So, yeah, I'm done.